Hi, welcome to Make or Repair. This is the Thermo-electric Temperature controller that I opened in a recent mailbag video. As you can see, it's an ILX Lightwave LDT 5910B. So the idea is that you will have some lab equipment generating heat, maybe a laser diode or something like that, and you use this as a cooler or heater to stabilize the temperature at some set point. I just finished fixing it, and in this video I'm going to show you that repair, and then I'll do a little experiment testing the temperature dependency of a germanium PN junction. So let's get to it. Now this is dead on power on, so nothing happens at all. Whether that's because someone's messed around with it or whether it's because it's just a very simple fault, who knows, but we shall dig into it and see what we can find out. The purpose of these really is to control temperature, as it kind of gives away on the lid, and on the back we have a pair of connectors here, or we can use this D connector to connect some sort of thermistor. Now thermistor is non-linear in nature, so an NTC thermistor onto there, and we can connect various sizes of thermistor, so 1K or 10K or 50K, whatever you want. We can control the current that's supplied to that thermistor using a switch here, and just here we've got something called TE module. So this is going to go off to a cooler or heater, so something like a Peltier device, something like that, where if you connect the power one way it warms up, if you connect it the other way it cools down, and yes, and it will essentially try and manage the temperature. So this should now just lever off. Oh, there we go. At the bottom, and yeah, we've got all the tilt feet and everything on here, so this is all good. And there's the bottom end access to our circuit board. Unfortunately, although I can find a user manual for this, yeah, service manuals are a different matter, but yeah, one thing at a time. Let's see if we can't figure out what's going on. And I am slightly concerned that someone may have removed a transformer from it, because I seem to have a lot of empty pads there, and there is some solder residue on them, although they don't look like they're horribly fluxy and horrible, but I'm guessing there should be a transformer right there. Oh dear. Okay. So, yeah, do I even bother to test very much more before I take that board out? Not really. Let's have a quick look at the fuse. Yeah, so the fuse is okay. So I'll just pop that back in before I lose it. Okay, I'm guessing this heat sink's here because this is a current source and it will source several amps. So there'll be some big MOSFETs or possibly Darlingtons on there, and there'll be a pair as well because it's bipolar. Right, let's see if we can't get in here and get these out. Awkward little clip. Okay, and there we have our power supply. So that, I think, is kind of like our analog section with its digital drivers for switching. And then we've got our digital section over here, and we've got our process here. It's a 80C188 is what it says. We've got 3 missing ICs down here, and I'm kind of hoping they are the GPIB, because the other device has a very large GPIB card, which actually sort of fills half of this case, and yeah, clearly that's not meant to go in here along with this power supply. Let's take a look at the power supply for just a second. So we've got our mains coming here on the black and white, and I'm assuming that these are supposed to be jumpers. That's a 24120 jumper, and this is a 24220, so that'll give me 240. I think that's how that's supposed to work. It runs through to this transformer here. But we've got an entire transformer section just here. It appears to just be missing completely. Yeah, there are 0 ohm jumpers on the back. Okay, let's start off then with volts AC. A quick probe around. So they appear on this filter to be just relying on the case screws to hold that together. Volts AC, yes. 241, 242, yep, that's fine. Just as expected, really. And then that's our primary on this side. So let me just turn this around so that my hands are away from nastiness. And we need to turn to volts DC. And so kind of as expected, we're not getting anything on any of those. Back to AC, and we'll just check the power's getting to the board, which it is. So we've definitely got no inputs coming into those, so yeah, we're definitely in the world of transformers. But actually that might not be too bad, because that therefore isn't the big heavy current source. Rectifier is diagonally opposite is its connections. There you go, we've got 16 volt AC coming in there. That's nice. Now can I get the other way around and get the DC voltage? Yeah, minus 21, but anyway, nearly 22 volts, so that's okay. So that seems to be my unregulated supply then. So let me think. So I want to see whether or not there's any life in the rest of the components on this power supply, and also it'd be really good to get some voltages onto the board. So what I'm going to do is I'm soldering some wires on in place of the transformer, and I'm just going to inject some voltages. So about 7 volts for the 5 volt side of things, and plus minus 17 for the 15015 side, and they're just a little bit higher because of course there is a bit of voltage drop in the bridge rectifiers, and then we'll see what happens when we get that transferred onto the main board, whether there's any life in this at all, because I don't want to go to the expense of doing a complicated transformer repair if actually there's no hope for the main board. So let's just see how it goes. I've got this the right now. Just double check. Yes, that's the tab. Right. Here we go then. So let's turn on mains power first. That's the unregulated supply. And then we'll turn on our 12 volt supply. And then we'll turn on our 5 volt supply. And oh! Well, we have something very different working there. Oh, look at this. Something's happening. And yet we can actually set the temperature by just dialing the dial. So I think this is feeling like it's worth pursuing in terms of, I don't know why it won't go below 10. Oh, I think I've got a limit set as to how low it can go. Okay, so there still might be some problems around that. I need to read the user manual to set everything up, and of course I haven't measured whether or not we can output anything. Let's see if I've got a thermistor. Okay, so I found a few thermistors in my drawer. This is an NTC 10K resistor, and I'm just going to attach that to the back and see what happens. Okay, so I've attached the thermistor, and there we go. Here's an actual temperature reading. Of course, I've just had that thermistor in my fingers, so it's cooling off. Let's warm it up a bit. There it is. Perfect. So it's definitely measuring temperature on that thermistor with no problem at all. So if we set our temperature, Okay, so I've tried to tidy the wires out of the way. So I'm reading a room temperature of 21.4, which sounds around about right, to be perfectly honest. It might not be right because I haven't calibrated this specific thermistor. And let's have a look. So that's my actual temperature just there. It's running in auto. If I click set temperature, we've got 16.8, and I can change that, of course, just by dialing in a new temperature. I can go down as low as 10. Now, why is that? Well, I kind of go lower than that because this should go down to minus 40, minus 50 or something. Well, if I press the select button, we can see we've got gain, and then we've got C1, C2, C3. So C1, C2 and C3 are coefficients applied to the thermistor to actually, because it has a curved output, non-linear output to temperature versus voltage, or temperature versus resistance. So that's kind of what these C1, C2, C3 are for. They're to put in different points on that graph, so we've got different coefficients in the equation, and we create a different curve to match the actual thermistor that we're using. So that's absolutely great. I'm not going to do that at the moment. The other thing I can do is I can limit the current, and this is 0.3 amps. So this is how much will be provided by the output to the heater or cooler. At one button. So I can also do limit TH, so that's limit temperature high, and one button, limit temperature low. Okay, so I've set up my load to 0.3 amps, which is what this is supposed to be limiting to. My actual temperature is 21.5, my set temperature 15.4. So what should happen is this should cool. And I'm delivering 0.3 amps. And that's it, it's just delivering 0.3 amps. 0.298 is what it's actually delivering. So I've got a set temperature of 24.5 now and an actual of 21.8. So I'm actually expecting this to work the other way around. Let me connect up my voltmeter and just double check that for, it'll only work for pulse, won't it? But should give me long enough. Yeah, minus 10 volts. Okay, so I will connect my load up backwards. Okay. Yeah, I'm drawing 300 milliamps. So I've got this showing red this time. That's showing red for heat because I've got a set point of 26.4 and my actual temperature is only 21. So if I warm this up, oh yeah, my current's falling and it's gone. And we've switched instead to a yellow colour, which presumably is cool, and now we've gone back to heat. Fantastic, that is working absolutely spot on. What I don't seem to be able to do is to program these parameters just here. So I need to have a little look in the book and see if I'm doing everything right. But generally speaking, if I can find a suitable transformer, then I will be laughing. If I can't find a suitable transformer, what I might have to do is to do a little patch, make a patch board, mount some other transformers on it, and go from there. Oh, there we go, got it. That's how you do it. Actually hold the button down. Right, okay, so if I select limit I, hold that button down. Oh yeah, there we go, look. Superb. Let's set it to 1 amp then. Now I shouldn't be able to deliver 1 amp because my load is only set to a little bit less than that. Let me set my temperature. Make sure that's nice and high. Check my actual temperature. Yeah, turn on the heater. And the heater has failed to be able to deliver its current. I think that's what that error means. So if I set my current to wish to draw, constant watts, I'm going to try and draw 20 watts. I'm delivering 1.016 amps. So one of my thoughts was that I could make a piggyback board that would sit on here, and I'd put a small 5-volt transformer and a small 15015 volt transformer on here, or 6 volts and a 15015, and that would provide all the voltages that I needed. And I was going to go with that until I realised that I am actually a little bit limited because this hangs upside down inside the main chamber. Yeah, I am actually a little bit limited for space. So I figured that what I would do instead is make a completely new board. Now, I did almost find a transformer that almost fits on here. So here's the transformer that I found. Hopefully you can read that part number. Let's try and get it the right way up. So here's a transformer that I found. Now, this is 30 VA, 5 volt and 15015 volt. So on this side we've got 5 volts, this side we've got 15015, and then we've got split mains for 240 or 120 volts, or 110, 120, whatever you want to call it. Now, this being a 5 volt secondary instead of a 6 volt secondary meant that when I sort of did the maths and worked out whether it would work with the 7805 that's sitting on this board just here, this 7805 is roughly at 300 milliamps, which is what we're drawing, has got close to 2 volts drop. So 5 volts multiplied by 1.4, less the drop, and that will not be regulating correctly. So I need to replace that with a different type of regulator. Unfortunately, although the pin out is in the right order on this, the pin pitch is not quite right. So I can't just literally drop this on, unfortunately. And on the primary side, this has got more taps than I'm using. So yeah, I would have to do quite a lot of nasty bodging. So instead, I have produced this PCB. Now what I've done in terms of the circuit for that is I've pretty much replicated the original. So I've been through here, I've traced through. Let's have a quick look at the circuit if I can. Right, so here's the circuit diagram. So this is pretty much the reverse engineered circuit. There are a couple of modifications that I made along the way, and I should say that this circuit, as we're looking at it now, does have a couple of revisions that I made after building this up and doing the repair. But I'll point those out as we go along, and hopefully it will all make sense. So I'm running this on a 4K screen, so I'm going to zoom into the relevant areas for you. So first of all, let's take a little look at this area. So this is the unregulated supply. So we've got a 15015 coming in here, and it's actually a 150, or it might actually be 120, I can't really remember for the unregulated. I wasn't really modifying those inputs, but yeah, they're connected in series, and we've got a center tap forming the ground, and there it is, P ground just here. So so that's fine, and that just runs straight through the middle, and ultimately that will actually join up through this little ferrite with the analog ground off the 15 volt circuit on the other part of the board. But for the moment we just need to know that we've got a simple circuit with no regulation. We've got a rectifier diode in the middle up here, and that is mounted on the chassis as a heatsink. It's about 5.4 watts I worked it out at, so yeah, that's fine. Nothing too much there. And the rectifier that I've put in is a GBU 806, which is completely over the top for this, but I just happen to have 10 of them in the drawer, so yeah, that worked for me. And I set out the board so that I could align this with the same hole that was used before. I did actually have to, this is a smaller less thick diode, so I did actually have to put a little shim in there onto the chassis just to take up the spacing, so an aluminium spacer. If we move on, we'll see there's a bunch of electrolytic caps, so 6,800 microfarads on each rail, and then another one. So that's over 13,000 microfarads on each rail. It seems a little excessive, I'm going to be perfectly honest, and then it's followed by a 10 microfarad and a 0.1 microfarad. And then we've got a 1 meg resistor on here, presumably just to notionally hold ground in the middle, I suppose. Doesn't really do anything that I can see, to be honest, just gives it a teensy tiniest little bit of loading. This isn't high voltage at all. It needs to deliver, of course, about 4 amps. These are very low ESR capacitors. They're only about 25 milliohms. Sorry. Yeah, that's not much, particularly with 2 of them in parallel. So now it is the case, of course, that with a capacitor working on DC, then you don't really get the capacitance that you're looking at here effective. But yeah, it still seems an awful lot for what it's doing. But I decided these capacitors were in perfect condition, and when I took them off and measured them, they were absolutely perfect. So I decided to keep those big 6,800 microfarad capacitors and just reuse them. I did replace the 10 microfarads and the 0.1s, of course, because, you know, they're 10 a penny in my drawer. Also, rather than working out a good value for the ferrite, I just recycle that as well. Let's move up to the top section where there's a bit more going on. So here is my input, and first of all we come in with the live and the neutral on the left hand side, and then we come across a whole load of little sockets and jumpers and things, and these are just the jumper points on the board, and these little large pins, PA1, PB1, PA2, etc. are just the pins going off to the chassis transformer. I just needed some way to make the sockets available for them. And then we have our transformer. So at the top we've got pins 11 and 12 are the 0 5 volt output, and then down lower we've got 7, 8 and 9 are the 15015. And as I said before, because this top lay is 5 volts and not 6 volts as I would normally use, we can't really use a 7805 anymore. The original board uses a 7805 regulator, a 7815 and a 7915, which are just, you know, off the shelf 30 pence each regulators, easily available from anywhere, and I put new ones in, of course. So same type of diode that I popped into the other part of the circuit, because, you know, I've got several, why not? And then we're coming along, and we've got a bunch of, so in the 5 volt line, which is this top one, we've got one of those 6,800 microfarad capacitors again, which again just feels over the top for a 5 volt line that's only drawing 300 milliamps maximum. So yeah, anyway, there you go. And we've got a 0.1 microfarad just on the input to it. Now that is not particularly needed, but you know, why not? Anyway, I replaced my 7805 with an LM2940CT-5. This is a 5 volt regulator, but it only has 1 volt dropout, so I don't have any problems with that lower input because we're using that different regulator. Same pin out, same current, everything's basically the same, it's just lower dropout. The other thing that is different with it, however, is this capacitor on the output. So on the original, this was a 0.1 microfarad capacitor on the output, and but because we're using a 2940, we have to replace that with a 22 microfarad, and that's because we require it for stability purposes. Anyway, that gives us our 5 volt rail regulated, and that goes across to this connector on the right hand side, which is of course exact pin out of the one on the board. Coming down, we can see that our 15015 is, you know, not really much different. We've got a 7815 in the top line. Now in the video later you'll see that I actually got the pin out on that wrong. I did blame it on Altium, but it wasn't their fault. I did actually wire that the wrong way around. I was moving things around on the diagram and just made a mistake. And at the bottom we've got a 7915, which is the minus 15 volt, of course. 3,300 microfarad capacitors on the input to both, and yeah, this is just a bog standard. So this is just a bog standard bridge rectifier going into a bunch of capacitors and into some off-the-shelf regulators. A little bit of capacitance on the output. Unnecessary, I think, are these diodes, which you would use, for example, if you were running relays and things like that, just to stop any reverse voltage, reverse current. But I'm not really sure what they're doing on here, but since they were in the original, I put them in. I've shown them as a 1N4001 on the diagram, but actually I just used a Schottky diode out of the drawer. Okay, and the other modification that I've made on here is resistor 3, resistor 4. So these are 2K7 resistors on the LM7815 and the LM7915. And the reason is, particularly the 7915 wouldn't regulate without this board. It failed to regulate below 4.5 milliamps of current draw. And that's what that 2K7 is basically giving it. Just a few milliamps of loading so that the regulation would be stable. Shouldn't really need that, but you know, maybe it's just the make of 7915 that I got on my drawer. It's probably 20 years old, I suspect, that I see. Anyway, so that's it. It's a ridiculously simple circuit, really. I've physically made this board exactly the same size, and I've put the mounting holes in the same place, I hope. And this is my first tryout today. Because they are slightly tricky to... oh yeah, that's absolutely perfect. So that's great. So that's great. All those mounting holes line up just spot on. And if we look on this side, just here, we can see the 7805 is lined up with the original mounting hole for the 7805 in here. And the bridge rectifier is also lined up with its mounting hole on the chassis just here. Now I do think this mounting hole here, which is for the bridge rectifier, I might have to just extend upwards a little bit, because I'm not going to try and reclaim the bridge rectifiers. And one of the reasons is that this bridge rectifier, I don't know if you can see, but the outer insulation has all chipped off and oops, and is broken. Not sure if that shows up on the camera or not really, but yeah, it's a bit of a cracked mess. So I'm not going to be reusing that is for sure. Instead, I'm going to be using these. So these are GBU 806s, which are considerably over specified. I think these are 600 volts, 8 amps. So ridiculously over specified for this job, but you know, they are what they are. And hopefully they will just drop in like that. Hopefully as well, I've got the pin out just right for the transformer. So I did actually get delayed ordering this board because I wanted to be absolutely certain about this transformer pin out when it arrived, because the data sheet was a little bit ambiguous about one or two factors on it. I wasn't too keen on that, but so I ordered the transformer, waited for it to arrive. I got that from DigiKey, by the way, and I was very unhappy. It arrived with these pins badly bent, because literally they'd put one wrap of bubble wrap around it, which of course these pins went straight through in a moment, and then chucked it in a plastic bag and just threw it in the box with all the other small components that I got, and it was rattling around on the flight from America, and yeah, not impressive really. But fortunately they did straighten. Otherwise, I would have had to make my first return to DigiKey, and they didn't have a lot of these in stock either, so I was a bit lucky there. Anyway, time to start assembling this board, I think. So I'm just going to, this is one of the key times when you want to start with your low components, because these capacitors are very, very large, and so is the transformer. And if I mount those first, although they'll give lots of stability, they're not going to make life very easy for me. I'm going to reclaim quite a lot from this board. Okay, so that's all the parts fitted, transformer in, voltage selection link in, mains connection on. I haven't connected up the other wires just yet, because I'm going to test it before I actually attach the various wiring looms. 1, 2, 3 that need attaching, and obviously then I need to bolt it to the chassis and apply whatever I want for heat sinking. Yeah, looks okay, I think. Looks very much like the original. The layout isn't quite the same, but because the holes are in certain positions, these two components had to be in exactly the right position, and I wanted to make sure that all these connectors along these edges were in identical positions. Now that kind of dictated that the layout that I produced was going to be very, very similar to the original one that the manufacturer produced. Anyway, I need to connect this up now and make sure it works before I plug it in to the main system. So I'm going to do some continuity checks to begin with and just make sure that everything looks sensible. Okay, so I've connected my main unit onto the mains. I'm putting it through here. Obviously I've got a switch on my main unit to apply a disconnect power, and then I've got my mains switched coming out onto my board. So that's off. I'll turn the mains on. And I've got my multimeter here in DC volts mode, ready to measure various voltages and see whether or not we have a working system or not. So first of all, crossing fingers. Okay, nothing blew up. This is good news. All right, let's connect to digital ground. See if I've got 5 volts or not. Don't seem to have anything actually on my multimeter. Just failed. Oh, seriously? My multimeter's just gone wrong. Unbelievable. Okay. That is just evil. Okay, so here we go. You may have seen this reviewed in a thing I did on budget multimeters. A video I did on budget multimeters. So VCC, if I remember rightly, this is the unregulated 5 volts going into the, so 13.9, that's a bit higher than I'm expecting. And there you go, 5 volts on the output on the 5 volt line, so that's nice. Of course this is under no load, which is why that VCC is so high. Okay, analog ground, I should have minus 20. Well, that doesn't sound right, does it? Plus 15, that isn't right at all. Nothing on there and nothing on there, because of course that transformer isn't connected up. Oh, so why have I got all of that voltage on here? Why are these voltages a million miles off? I think it was 50 degrees. This one seems fairly cool. Coolish, yeah, not too bad, but that one there is definitely toasty. Maybe I'll put my 7815 and 7915 the wrong way round. Possible. Definitely backwards. It's definitely in on this side and out on that side. And my screen print is most definitely the other way around. So, plus 15, minus 20. So the only way I can think of and get minus 20 is, well, could be something to do with the capacitors, but is actually if I'm shorting here, maybe. So through diode 6, is that connected backwards, maybe? In some ways, I'm kind of glad that this has gone wrong, because it demonstrates the issues with building your own circuit, and also the stuff that happens along the way. So diode 6 on the printed circuit board appears to be inserted the right way around. It would be good to get a little bit of load on this, maybe. Maybe it's not regulating simply because it's has insufficient load. So let's very carefully then attach a couple of test these here, and then we'll just connect those onto my DC load. Oh, hang on, let me make sure we've got these the right way around. No, the other way around. It's being a negative voltage. Yep, and currently I'm showing 1.2 volts, that's just a capacitor discharging. And we will set it to 0.05. So we'll set this to 50 milliamps and just see what we get. Turn that on, nothing happening at the moment, and turn the power on. And we get 15 volts. Oh dear. So now it's regulating, now we actually have some load on it, so that's good. Let me just double check that with the meter here so you can see it. There's ground, and there's your minus 15 volts. Okay. So interesting to see, I think, at least. I think it might be interesting to see just at what point. So it's losing the regulation at about 4 millivolts, something like that, maybe 5 millivolts. And the regulation is pretty poor, to be perfectly honest, down at that end. But anyway, that's around about what's happening with that 7915. So I had got it in the right way around originally. I've wasted 3 regulators along the way here. 17815 and 27915, but oh well. Chalk that up to making a mess of things. So I will silastic these together, put a little bit of silicone in here just to hold these together so that they form a more positive thing, and I'm just going to put some nylon nuts and bolts on here just to hold everything in place. I just need to go and find some washers. So everything's up and running, and I'm going to run a little experiment, I've decided, just to demonstrate how this thing operates. So first up, a quick tour. On here we can control the limits for the upper temperature, the lower temperature, and the amount of current that we use for cooling. So this is going to a thermoelectric cooler. So that's a semiconductor, so the amount of cooling we get will depend upon the amount of current that we source through that semiconductor. Now, if we reverse the power, then instead of cooling, it will heat. Now, I set up a little thermal chamber over here, and in it I've got a PN junction, in other words a normal diode, so a germanium diode as it happens, and I've also got a couple of wires coming out because I've popped a thermistor in there. Here is my cooling unit. So the cooling device is actually sandwiched here between these two heat sinks. So this one is designed for actually when you're cooling this side down, you might need to shift a lot of heat out of here. When we're heating, it's not such a problem because, of course, we're controlling the amount of heat that's appearing on this side. So if it gets a bit hot, we're just reducing the current. So that's not such a problem. But when we're cooling, we might need an awful lot of energy going into that device, and yeah, that will need a lot of heat sinking and active air movement to get it out of the way. So this is going to go into essentially this thermal box through a lid, and I think we'll fit it in that way around like that. So here's our lid, and that's going to go on here, and hopefully we should then be able to cool and heat things down a little bit. Now I do need to, I think, perhaps stretch my cables a little bit. Yeah, there we go, everything's connected up. So at the moment we're just measuring the temperature inside that box, and hopefully we can move that temperature around a bit. On here we've got my little component tester. Now the bonus with this component tester is that if I switch screens, it connects to the PC, and we can actually plot a graph. Okay, we are ready to go, I think. So the output of this is connected to the Thermo-electric device. It's measuring the actual temperature at the moment. Let's do a set temperature. So I've got a set temperature of 0, so that's going to be interesting. See if we can reach that. And here's our active cooling button here. So I'm just going to turn it on, and it will switch to cooling. And while I'm doing that, I'm going to connect up a couple of cables to run my fans, because it's not going to cool the inside of that box very well without any moving air. So there we go. Our temperature is dropping happily. Let's see how far down it goes. This is not, of course, the best of compartments, but fingers crossed. This is helping it. Now this, you hope to obviously just hear, limb I is flashing. That indicates it's attempting to cool as much as it's allowed. So I've got the current limit set to 4 amps on this, so it's pushing 4 amps through that thermoelectric unit, and that's the maximum it will be allowed to go. So it might be that we don't get to 0 degrees, but we'll see. It'd be good if we can. And then what we'll do is elevate it to 10 degrees, 20 degrees, and so on. I will, of course, cut some sections out of the video so it's not too tedious for you. So we've reached 10 degrees, which is actually one of the points I want to test. So I'm just going to actually just run a test on that now while it's there. Why not? And there we go, there's our curve at 10 degrees. So I'll just change this label to 10. Not A10, just 10. So I'm just going to leave this to try and keep cooling, see if we get to that magic 0 or not. Okay, I seem to have reached equilibrium at about 8 centigrade, and I need to go a fair bit lower than that. What I found is if I sort of press on things and close up the gaps, then the temperature goes a bit lower. So I think I've just got an equilibrium with the air leakage around this unit, and yeah, and the ability of the cooler, which is running considerably underpowered. So I think overall, if I take this up, I'll hopefully get a little bit lower. Okay, so I have stuck a bit more tape around some of these seals and taped down the top a little bit tighter, and because it was stalling at about 8 centigrade and it's come down to 3.4 now. But I think with such a crude refrigerator, that's about as far as I'm going to get. So I'm going to just run my next test at 3.4 centigrade. So here we go. So if this is, you know, a lot of thermal dependency, then we should be able to see a measurable difference between the curves. We're seeing a fair bit of difference there. So the red one being 10, and I'm going to just rename this label. I thought I was going to rename that label. I think I've deleted it by mistake. So this is 3.4 centigrade. Okay, so that'll do nicely. Okay, so 3.4 centigrade. It has achieved quite a lot of cooling, but the limitation isn't this. The limitation is this rather poor quality. So let's turn this now up to 20. Interesting to see how well it copes with that. So I've done 3.3, and now I'm going to do 20. Just lock that in. And we can see on here that this has switched to heating. And look at that, temperature coming up nicely now. Of course, it's in a box where the actual box itself is cool and everything, so that is going to be cooling things off. So it stops at 20.6, so there's a bit of an overrun, 20.7. So it is still heating, but the temperature is dropping, and that's because the surface temperature of all that polystyrene around it is, of course, quite cold and still holding that temperature down. So let me get ready for when this reaches 20, and so if I turn the gain down, then that wouldn't have approached quite so fast and wouldn't perhaps have overshot quite so much. But you know, that's pretty decent. I'm not too worried about that. To 30. And there we go. Temperature 30, and of course we should see it heating now fairly swiftly. So working well, just kind of probably just yeah, okay. So it's actually heating, but it is losing temperature, and it's either leaking air to the room or the surrounding polystyrene is so cold because it's been held at, you know, sub 5 degrees for an hour or so. So it's just working on it, just trying to recover without going over the top. So you can see the recovery is really slow, it's really tiptoeing around there, but it's still applying heat and it's barely gaining temperature. But as I say, that's because that polystyrene, expanded polystyrene around everything is at fridge temperature at the moment still. I mean, it'll warm up fairly soon, but yep. Okay, so let's get ready and I will prepare for my next reading. So if things go as they have so far, we should be seeing another reading to the left of this one. And there we have it. Nice. And we'll just rename that. To 30. Okay, so now let's give it a bit harder work to do. And we'll wind up to 40. I'm going to leave it at 40, that will be my highest one, because I don't actually want to damage my cooling device. I'm sure we'll go a bit higher than that, but I don't want a surface sitting at 60 centigrade or something like that. Okay, so it is actually struggling to reach its 40 centigrade, and again, not really a reflection of this, but a reflection of my construction over here. I'm going to take my reading at that point then. 39.9. 40. There we go. So that's handy. So I'm expecting it will hang around pretty much at that, maybe 0.1 either side. But let's run my 40 degrees. There it is. And I very much doubt my ability to get this to 50, but we'll give it a go. So we're throwing out as much heat as we can into this compartment at the moment, but I think it's just not going to cut it really. Some difficulty keeping it there because look, I'm very close to it and I'm still running at full power again. The temperature just dropped off a bit and it threw a bit more power in to try and help it along. 49.8. Okay, 49.9. So the casing is heating a little bit more, so let's switch across and take our measurement. And that's a very, very faint line, but it is there. I'll change its colour in a second. Okay, so there you go. I've turned the output off. So once you turn the output off here, it's actually safe to do things like connect and disconnect things, so that's really helpful without disconnecting the whole thing. But what I could do, of course, to bring this down to close to room temperature is I could, of course, reset the temperature to, let's say, room temperature-ish. That's met at about 20 degrees, that'll do. Okay, and it's doing nothing at the moment, it's just cooling naturally. We'll turn that on and see if that speeds things up a bit. There we go. So now this should come down fairly rapidly to the 20 degrees and actually sort of hold it around about that temperature. As we give it more time and as we tune the gain, then we'll be able to make it stable. Anyway, in the meantime, let's have a look at our experiment result. So here is the result of running our germanium resistor at different temperatures, and as we can see, there's actually quite a sizable difference, and I'm going to put a marker on in a minute, I think, if I can manage to figure out how to do it, to actually kind of show us that. What I think I'll do, so obviously they all start around about the same, and we start picking up about 0.2 volts or so, but of course the conduction at this point is really, really low. But let's take a look then at, I reckon, let's look at this region just here. There we go. So this one on the right hand side, which is missing its label, I'm presumably hidden it by mistake, unhide label, is 3.4 centigrade, then 10, then 20, 30, 40, 50. And to some degree they're fairly evenly spaced out. Okay, I've dropped a couple of lines onto this, a couple of arrows, and done a few calculations just to try and make things a little bit clearer. So looking at the baseline on this graph, we've got a forward current of 9 milliamps, and our forward voltage drop though varies quite a lot. So it varies between 1.36 volts and 1.52 volts, thereabouts. And I've done a bit of maths, and that works out at a variance of 3.43 millivolts per degree C. I've written volts per degree C on here, and that's wrong, of course. Now we can also look at it on the vertical, and we could think about keeping forward voltage the same at, say, 1.5 volts. And we can see on the graph that that will vary between about 9 milliamps and 12.5 milliamps. So that's quite a lot. Now, if we look at voltage forward drop at a common temperature, so let's say 20 C, I've written 25, I meant 20, we get a 2,325 parts per million temperature dependency on this particular device. So hopefully that was quite interesting. So there we have it, a fully working device. I had to completely rebuild the power supply, of course, but it wasn't anything advanced, and buying a suitable transformer was far better than trying out some sort of bodge with multiple small transformers. Now, although crude, my little experiment hopefully showed it in action and was quite interesting. And as usual then, if you found it interesting, please like the video, don't forget to subscribe and comment, and that's it. Bye for now, see you soon.